Welcome DC Circuit students. In this mini lecture we're going to use the TINA TI circuit simulator to look at the impact of internal resistance, which limits the ability of a voltage source to deliver all of the current that your circuit might want, and also how it affects the current through your load. In an earlier video, we did this on the protoboard using two partially discharged 9-volt batteries to create a voltage source with a reasonably high internal resistance. And we were able to show that by putting two of these limited voltage sources in parallel, we were able to deliver more more current to a low resistance or high load, high current demand circuit. And in that sense, for that situation where we had a low resistance in our load circuit, we were actually being limited by this internal resistance in series with each battery and got a benefit from putting two sources in parallel. So we're going to continue to explore this with a simulator where we don't have to worry about overheating a resistor, and we can really get a good idea of how much current will flow. So right here we have three circuits, all with a fairly high load resistor. So it's a low load circuit in terms of low current draw. So in these cases, we are expecting the source being in parallel or not, a single source, not having much effect on the current through the load, because in this case, the load resistor will control, and we have to follow Ohm's law. And we would also expect this internal resistance, when we put two sources in series, to have a negligible effect on the actual current that flows through our load versus what we would calculate for a no internal resistance. So having built our circuits, let's run our DC analysis and see what we get. And to simplify, I'm going to turn off some of this data. We're not concerned with node voltages right now. And we've labeled the load resistors so we don't have to look at the current drop over all of our different resistors. TINA gives it to us, but we're really concerned with the current through our load resistor, which is our circuit. So let's start with our single source. So it's telling us that the current through our single source is 1.53 amps, and we can look at the effect of that 25 ohm, I am assuming we have in all cases 25 ohms of internal resistance in our sources. So this battery symbol with the 8.63 volts is representing a perfect voltage source, one that can give you any amount of current you might want, and it's going to deliver it at 8.63 volts. Now this 8.63 matches the open circuit voltage of the 9-volt batteries that we were using in our protoboard video. If you'd like to watch that, recommend it if you haven't. And the 25 ohms is representing the actual resistance within the source itself. So this is, I would call this a compromised source. So its actual voltage that it delivers at, which the circuit would see, which would be the voltage at this point right here that I'm kind of showing with the pointer, would be current dependent, depending on how much current was flowing and how much voltage we dropped over that 25 ohm internal resistor. But if it weren't there and we had a perfect voltage source, we would expect a current of 8.63 volts divided by 5,600 ohms. We'd expect 1.54 milliamps, and in fact, due to the 25 ohm internal resistance, the non-perfect source, we got 1.53. Pretty close, not too much. Let's look at the current that we got through our load when we put two of these partially discharged batteries, or real voltage sources with internal resistance, both 25 ohms of internal resistance. And we put them in parallel. Now we're still driving this load resistor. Now I'm looking up here at this other load with our parallel real voltage sources. We put these two in parallel. So we're going to be driving this load with whatever the node voltage is up here. And this is a little bit more complicated circuit, and we could use superposition, which is a network analysis method, to get the node voltage here and figure out, then apply Ohm's law to see how much current is flowing, and we'll do that in another video. But for now, we let the simulator do that. In fact, that is what the simulator actually does. And we can see that if we use two sources, we actually do in fact get the theoretical current through the load. So that's an example. It's not very dramatic because 1.54, 1.53, not too different. But you're beginning to see now the benefit of the current delivery capabilities of a parallel configuration. We haven't broken Ohm's law, but what we've done is partially accounted for the fact that a real voltage source is going to have some internal resistance. And so by putting two together, we were able to actually achieve what Ohm's law would have predicted in spite of the fact that we have this resistance. Now if we look at putting those two real voltages in series, we get sort of a little bit different effect. Now we're looking at the current through yet another load. same resistance, 5.6K. And in this case, we could just apply Ohm's law by bundling the resistors together. So we're getting, if we look at this, we're seeing we get 3.05 milliamps through our load. If we were to say, okay, what was the theoretical if we didn't have the internal resistance, we would just go 8.63 times 2, 5,600 divide. So we would have expected to get 3.08 milliamps. But because we've added 50 ohms of series resistance, we've throttled down the overall current going through all of the batteries and or whatever our voltage sources are and the load, and we've seen a small reduction. So if we were to calculate the voltage drop over that resistor, of course it's going to be lower due to the lower current. We still got, if we were to calculate the voltage up at this node, at this corner that I'm kind of circling, it would still be fairly close to our theoretical of 17 some odd volts. We wouldn't be seeing a tremendous reduction. In fact, we can calculate just using our TINA. We can back that node voltage out without opening up node voltages. We know that we have ground here. We know that we have 3.05 milliamps flowing through that 5,600 ohm resistor, so we can figure out what our node voltage was there. And I'm doing this on my calculator live, so please excuse. 3 minus times. So we would have had a node voltage of 17.08 as opposed to 8.63 2 times instead of 17.26. So that's still a what would be a measurable reduction in this time in voltage that's dropped over our load resistor. So we typically put sources in series to get a voltage boost. They're additive, their voltages are additive, so we're seeing that reduction in what we would have gotten theoretically by adding the two together. So just to recap, before we move on to a higher current draw circuit and see if we can't make this a bit more dramatic, these differences, we are modeling effectively the effect of an imperfect source by simply adding a 25 ohm resistor in series with a perfect DC source. So this again would be modeling a low current delivery power supply. Most battery systems, certainly any battery system that is operating at a very high current compared to what it is rated for, or a partially discharged, especially primary electrochemical system. Okay, so up till now, we've chosen a load resistance that gives us a very low current draw. Our circuit's not really demanding much of our voltage source because its resistance is very high compared to the internal resistance of our sources. So let's swap out that circuit to one that really is going to allow a lot of current to flow. And I'm going to do that by going in and changing the properties of my load resistors. And instead of 5.6K, I'm going to change them to 50 ohms. So 50 ohms is very low. So this would be like a heating element or a motor or something that really wants a lot of current. Is hopefully designed for it. Hopefully it has a big heat sink, not our little quarter ohm or quarter watt resistors. Okay, so now we're going to repeat our DC analysis. We're going to get rid of all the stuff we don't really care about. In case you're not familiar with TINA, these numbers that appear when we run the analysis refer to analysis nodes. So if you do a nodal analysis in your network analysis and start looking at those points in the circuit where you're combining currents and looking at voltages, that's exactly what the program is doing, and these are those same exact analysis points that the program used. And if you are displaying node voltages, as I just did, clicking, just giving a little TINA preview, these are the voltages versus ground, versus wherever you put your little ground in each of these circuits, and they've named the program's named it consecutively for all the different circuits that you use, so you could find that for everything if you wanted. So now let's take a look at, and first we're gonna compare our single source with our parallel source. So now we're gonna check out the current through our single source, where now the load resistance is only double the internal resistance of our source. So we're seeing 115.07 milliamps, where 8.63 enter 50 divide. We would have predicted if we had a perfect voltage source, we should have gotten 172.6 milliamps. So it's pretty easy to tell that what we've done is we've raised the total resistance of our series circuit by 50% just before we ever got out of our battery. So that was a significant hit in the current delivery capabilities of this source because of this 25 ohms of internal resistance. So now remembering that 172.6 milliamps is basically the perfect uninhibited current that we would get with perfect voltage sources. Let's look at how much closer we got to that by ganging two of these real imperfect voltage sources in parallel. And we do that by looking at the current through other load. It's our other load resistor. Now, because we had two voltage sources, we were able to get 138.1, rounding off to one decimal place. We still couldn't get what we would have gotten with a single perfect voltage source, but we came closer. So that's a more noticeable and dramatic example of the benefit of putting multiple voltage sources in parallel. We haven't broken Ohm's law. We're still being limited by whatever the node voltage is up here, but what we're doing by running multiple sources in parallel is we're raising this node voltage that I'm kind of circling up here. And the higher this is, of course, we can apply Ohm's law, the more current will flow through our load resistor. Okay, so let's go back to our sources in series, and let's recalculate 2 times the current to beat for a perfect source. So we would be looking at 345.2 milliamps if we had no source resistance. So we're looking at the current through yet another load, 50. But because we had ultimately 50 ohms of internal resistance, the same as our load circuit, we got about half that. So we had a dramatic reduction in our current delivery capability, even though we were driving this circuit with double the voltage. Because we had such high internal resistance in our sources, we doubled effectively the resistance of the circuit. So even though our circuit had a very low resistance and should have permitted a lot of current to flow, we weren't going to get it. And we could have kept adding sources and raising this voltage point here, but every time we added another source, we would add, in series, we would have added more resistance. So this gives you an idea of why a low internal resistance source or a high current capability source is so important when you need to deliver a high current to a low resistance type of circuit like a heating element or a motor or something that's going to consume a lot of energy. So that is it for our simulation, and the next and last video here we'll do a preview of superposition and use that technique to do the hand calculations that Tina's doing behind the scenes to calculate things like a node voltage with multiple sources that we might have in parallel or in series. And if we find ourselves without a simulator, or just because we need to know how to do this with math ourselves, we'll learn how to calculate these node voltages by for any number of sources, so we can figure out what the impact of putting another source in parallel or not, and is it going to be worth it, depending on the resistance of our load.